Swayam Prabha. Digital India. Educated India.
Welcome to the NPTEL course on building energy systems and auditing. Today we are in the module number 3, and the first module of the first lecture of the module number 3 will be delivered today. The module 3 will be based on the building heat load estimation. So, we will discuss 4 to 5 type of the modeling strategies. So, in the lecture number 11, we will start with the very basic steps, computational steps of heat gain, and we will discuss the heat gain through conduction method. We have some kind of idea that we have already discussed that one in the very first chapter. We will discuss the concept of overall heat gain coefficient, and also due to the solar radiation what is the heat gain changes and all. So, first of all we will start with a flow chart. So, in the computation, the heat load computation, the very basic or preliminary type of computation, what we will actually going to require is that the area of the surfaces or the envelope. The area of the surfaces or envelope, if I want to say, that means it is the area of the wall, solid wall, opaque wall, the area of the roof, and also the area of the windows, doors, etc. So, altogether this area of the windows or the door, any fenestration, that may be a glazing also, that may be a curtain wall with some kind of a transparent material, those comes under the fenestration area, and there is definitely a horizontal area of the roof and also the wall. So, from the different envelope, depending upon the material and depending upon the exposed area, the heat will gain or heat will actually inducted inside the building. After that, we need to also justify or classify the what are the different thermal property of those material, those opaque material, what is the U value of the material basically, and also the what are the U values of the roof also, or maybe the windows. And finally, we will compute with this equation. This equation is also known to us, that the area, corresponding area is multiplied with the corresponding U value and the temperature difference between the outdoor and the indoor, that will finally give us a Q, that is the heat gain in watt. So, we will take a straight away a small problem, and let us see this how these steps can be taken into account. So, the profile of a particular building is given as 12 meter by 10 meter is the plan area, and the windows are also mentioned. There are W1 and W2, the height and width of the windows are also given. The W1 is 1.2 meter by 1.2 meter, W2 is 1.5 by 1.5, the height of the room is 4 meter I have kept, and the outdoor temperature is 38 degrees centigrade, let us assume for a particular time, and let us assume that is a steady state flow, and indoor temperature is 24 degrees. So, there is a temperature gradient exists, and I need to give another set of data, that is what are the U values. So, the U value data of wall, window and roof are given 2.13, 5.23 and 3.59 as the values of U value of those three materials. So, then first of all we have to actually take all the north, east, south and west direction, and also directions are also mentioned over here. The longer sides are in the north and south. So, the north and south wall are of 12 meter by 4 meter, because the height is 4 meter, whereas the east and west are 10 meter by 4 meter, and the roof is 12 meter by 10 meter. So, those L and H are mentioned over here in a column. The window 1 and window 2 are also given. So, how many windows in how many faces? Suppose if you see the north face, there are no W 1, there are 4 W 2. See in the this particular the figure, there are 4 W 2s in the north and there are 2 W 2 in the north and south and 2 W 1 in the south. So, like that these things are separated. So, finally, what I came to know from this particular chart is the wall area and the window area. So, I have written it down in another table. So, the north facade, the window areas are 40.8 meter square and 7.2 meter square is the window, which is these two values. Like that, the east facade is 34.96 and 5.04 like that, and finally, the roof is 120 meter square is the roof area, whereas there is no window in the roof. So, now I know all the areas. So, I can just add up all those areas. These are the areas of this 4 wall area. Wall is opaque. So, from 40.8, then 34.96, 41.52 and 37.12. So, those are the summation of all the wall area multiplied by the U factor, U value of the wall, which is 2.13. I have mentioned in the very first slide, and this is the del T. So, this is the del T value, this is the U value, and this is the sum of the area. So, and if you just multiply this, you will get 4604 watt. Similarly, the window areas are also being added up over here. So, this is the area of the window, and this is the U value of the window, this is the del T same, and then the value is this 1581, and heat conduction through the roof is 120 is the area. So, this is only one patch of roof, this is the U value of the roof delta T. So, the 6031 is the heat gain through the roof. So, this 3 now can be added, very simple, this 3 can be now added, and then I found out that this is 12,216.96 watt. So, 12.22 kilowatt. So, that means almost 3.5 tonnage of refrigeration. So, this conversion is how. So, I have divided this 12.22 divided by 3.5 is your the TR from kilowatt to TR. So, now I have a Excel sheet. So, the conversion from the kilowatt to the tonnage of refrigeration we can see. Now, we can go to a Excel sheet, and in that we can see that how it can be calculated. So, in this Excel sheet, if I give the length and the height, suppose the length of the north facade is your 12 and also the south is also 12, the east is 10 and this west is also 10, the height is 4, I have already kept it as that. So, 12 and 10 is the dimension of the roof, and the numbers are maybe this is 0, this is 4, and let me check with the other numbers. So, this southern side is 2 2. So, southern side face it is 2 and this is also 2. The eastern side it is 1 2. So, eastern side this one is 1 and this is going to be 2, I think 1 2, and this is 2 0 in the western side, this is 2 and this is 0. So, ultimately you will get the total chart ready, and then the values of your from the north facade it is 1.744 kilowatt is your heat gain. So, this graph, this particular graph will show you, this bar chart will show you the heat gain through different envelope from north, east, south, west and roof, and this pie chart will give you the percentage. So, roof is the maximum 51%, the heat gain is through the roof, and this is the other side, but here I have taken only the outdoor temperature and the indoor temperature difference over here. You see, and this is the place where you can put your values of the U value of the wall and U value of the roof, U value of all the window values. SHGC values we will take in the next and we will see. So, in the PowerPoint presentation now, so we have this chart ready. So, whatever we got, the final value is 12.1 to 12.2 almost your the value of your the heat gain through the conduction or so, and 3.5 is your TR. So, that on this particular chart we have shown just now. Next is a concept of the overall heat gain factor. So, if you see, as we have just now calculated, the first these terms 154.4, 21.6, those are the 120, those are the surface areas. If you add them, you will get 296, which is equal to your the total envelope area. Okay, this envelope area, this is the perimeter into the 4, and this is your going to be your the area of the roof. So, the total 296 is your the envelope area. I think we have to multiply this with 4 because the height is 4 meter or so. We will correct it in the when we distribute it to you. Now, next layer, if you see, this is your respective U values of different the portion of your envelope, that is 2.31 is for wall, 5.23 is for windows, and roof is 3.59. And finally, that part, this last part is your delta T part. Okay. So, if you see this, if the product of the area into the U value, and if you take the temperature difference, this product of the area and the U value is called the overall heat gain coefficient. So, that is the kind of a criteria, the heat gain criteria of the envelope. If this overall heat gain coefficients are higher, definitely it will admit lot of heat, more heat. So, that will give you a kind of a health of a kind of a building. If it is low, then it will not going to admit that much, right. So, and this overall heat gain coefficient, which is multiplication of the corresponding area and the U value of the different material of the envelope, is a kind of a scenario which comes from our architectural design of the building, because surface areas and all I am going to decide upon, and also the material U value multiplied by the temperature difference, that if I multiply with different temperature difference, I will get the different heat gain coefficient value. So, whenever this architecture of the building is fixed, this OHGC is fixed. Now, in different days temperature, it is always not going to be 38 degree, in the evening time it will be less, in the morning time it will be less, in the some other month it will be maybe more. So, like that the 38 may change to some other degree. So, delta T will going to change, but each time I will multiply with the OHGC of the building, and I am going to get the total amount of heat. So, this OHGC in my case it is 872.64, and with the temperature difference, if I multiply with your the 14 degrees in my case is for the 38 minus 24 is the 14 degree difference in this my case. So, directly if I multiply, I will going to get this 12.22 kilowatt, which I got by breaking down all the things. So, summation of all these things, as you all know, this is going to be a 12.22 kilowatt. Otherwise, I can actually go through the OHGC factor. So, now suppose the temperature I just now told you, I mean this temperature has changed, instead of the 38 degree, it is 40 degree outdoor temperature, and indoor temperature I kept as 22 degrees. So, the temperature difference is 18 degrees. So, what I will do? I will just multiply the OHGC with your delta T, which OHGC is your 872.64, and now the delta T is your, this is your delta T, which is now little higher 14 degree to 18 degree. So, your total admitted load, heat load is more than 12, 15.71 kilowatt. So, if I will try to model a particular building based on that outdoor temperature only, nothing, no radiation, no other kind of the scenarios, only the outdoor temperature, indoor temperature, it is best to go with the OHGC. First compute the OHGC and see the scenario changes in the hotter month or the summer month or the winter month or so, the average temperature or whatever may be. So, now next let us see the heat load computation with the solar radiation. If the solar radiation come into the panel or the building, different panels of the different surfaces of the building, also the roof, then what will going to be the change. So, I have given the 3 solar radiation phases. Suppose in the morning 10 o'clock, the sun angle is such a way that the azimuth and the altitude angle is such a way that only the east facade is receiving 150 watt per meter square radiation, because you know the radiation unit is watt per meter square. South is getting 75 watt per meter square and the roof is getting 30 watt per meter square. North 0, no radiation over here, and west is also 0. Now, at this particular point, suppose the north and west are 0, they are not getting any. So, I have to give some additional data to model this one. I have to give SHGC, because I need to give SHGC, because due to the solar radiation there will be some the heat will be admitted through the window by radiation. There will be some kind of the absorbance and the surface conductance. From there I have to find out the solar air temperature, which actually the body temperature of the outside wall, and the heat transfer will take place or the heat conduction will take place not because of the outdoor temperature, but because of the outdoor surface temperature. So, I have to go to a new the flow chart, where I have to first compute the solar air temperature by virtue of this equation. This equation also has been discussed in the very first module. The outdoor temperature plus something plus I into A by F naught. A and F naught are the surface conductance and the surface, the absorbance and the surface conductance, and instead of the TO A, I have to take the solar air temperature over here. So, this has to be taken, and also additionally A into SHGC into I has to be taken. I here is the solar radiation. So, I know this particular the adjustment, the solar radiation adjustment has to be taken into account for the east, south and the roof, because these 3 surfaces are having some kind of a solar radiation as per the data given below, given in the last slide, but north and west will be remain as it is, because I value is equal to 0. So, solar air temperature will be equal to the outdoor temperature as 38 degree. So, I have did the calculation. So, I have given 3 sample calculation for the north wall. So, north wall as solar radiation is 0, you see the solar air as the radiation is 0, the solar radiation is 0. So, the solar air temperature become the same as the outdoor temperature 38 degree, whereas in the south facade the solar air the solar radiation is 75, that is the I value is 75, this is the TOA, and this is the absorbent for the windows, and this is the F naught for the windows. So, there is a little hike in the temperature, instead of the 38 you have to take 40.5, you see. So, similarly for the east facade it will be 43 and the roof it will be 43.6. So, the roof the I value is this much 300 or something, and then the absorbent A and F naught are some different values. So, there is a almost the 5.6 degree the hike in the solar air temperature. So, that has to be taken, and the T in, what is T in? T in is your indoor set point temperature 24 degree, and your delta T will now going to change for wall and for the windows and for the roof and all those, and everything has to be taken into account in your the equation number, this equation now, where everything has to be multiplied multiplied by corresponding surface area and the u value. So, with the Excel we can did it, we can do it very easily. So, and that particular value if you read here, suppose if I just see the heat conduction to east wall. Now, east wall area is you know this is the east wall area, this is has to be there is a equal sign over here. So, this 34.39 is the east wall area, 2.31 is the this is the area, this is the u value, that will remain same, but here you see this is your T indoor and this 41 degree is T solar air at temperature. Okay, so, now you are getting a different value of the Q. Similarly, heat radiation through the south window will be the A SHGC into I. So, the SHGC factor has to be taken into account. So, this is 397, 397 is the south facade and this is through radiation. So, this is your A into SHGC into I and this is your heat conduction, that is your the A into U into this del T, and this del T is this difference between them, this is your del T, this is your del T right. So, I am getting heat conduction through all the surfaces, I am getting heat conduction to wall, window and also roof for all the surface, all the facade, and this one heat conduction to the east wall it is 1265. This is this what I have actually calculated or just as a token of kind of the explanation. And now, if you add up, so if you add up you will get the total heat conduction through those 5 surfaces starting from the north, east, south, west and the roof, plus these 2 values will be your total heat conduction for the radiation through the window, because the only the east facade and the southern facade is having the solar radiation. So, total solar radiation due to conduction and radiation will be something like this, and again if you add up the sum, this is the sum, it is going to be your 16.81 kilowatt. So, almost like 16.81 16.18 kilowatt or something. So, we can see in the Excel, So, I have given the facade data. So, for that it can be now is 16.51. So, if I do not give any this the values, if I put these all values as 0, so 0, 0, I will get 12.48 for 46 or so. So, only for the conduction I am going to get the values, but if I just give some, suppose if I give some north facade value, suppose the north is maybe 100, the east is suppose maybe 200 or something, and roof is suppose 250, I will get some different value. Okay. Suppose in some other time, suppose in the afternoon time, this north is going to be 0, east is also going to be 0, south facade may have 300, the west facade may have 250 and this roof may be of your 400, then you will get some different values. So, you can change the parameters, you can change the values, you can also change, suppose on this particular case, if you want to see the, if I just go for suppose let us read this one as a 19 point something, 19.26 is the total gain of the heat gain, and you need 5.5 TR tonnage of refrigeration of your the total amount of the heat, the air conditioner required for this room. So, now if I just provide a better material, suppose 1.5 is the material value of the wall value. So, see it is changes, it goes down by 17 from 19 to 17. Suppose you further improve the window value from 5 to 3, 3.5 maybe 5 to 3.5, further it will going to give you the reduction in the total heat gain from 17 to 16.8 or something. You can also improve the SHGC value maybe 0.3 or something over here. So, again there will be further decrease in the heat gain. So, this is a very interactive chart, and you can actually use this chart. I will send this chart through our the discussion forum, and you can actually go with this particular chart. And suppose in this particular cases you just decrease the internal temperature. Suppose the set point temperature, internal set point temperature is, you are comfortable with 20 degree, not 24 degree. So, what is going to happen? The total heat load will increase or decrease? Total heat load will increase. So, from 15.57 it is definitely going to be increased to the 18.57 also right, because I am internal temperature, set point temperature I am decreasing from 24 to 20 degree. So, suppose outdoor temperature is very hot, instead of the 38 degree it is suppose 42 degree or something, very hot summer days. So, definitely it will going to improve or increase. So, it is now 18.57 degree. So, it is a very interactive chart. You can change the peak value of your the solar radiation, and just to find out the what will be your total tonnage of refrigeration required for your this particular room, and you can have the set and absorption values, you can have the surface conductance values that you can keep, and this chart you can see the different conduction values and the radiation values and the total conduction plus radiation values for your heat load, and the pie chart and the bar chart is going to be help you. So, again let us go back to the PowerPoint presentation. So, here we have that particular discussion that what we got if I take care of the radiation also in the surfaces. So, the nutshell is in this particular the discussion is that the total the building envelope through the conductive and the solar radiation has taken into account, and cooling load is estimated, cooling load is explained, and we have explained one very important criteria is the overall heat gain coefficient, which is a very easy way to understand, but definitely it is a kind of that kind of a the approximate way to find out the thing that the heat gain coefficient. We will take this particular the overall heat gain coefficient in the next lecture to see how that will help us to estimate the heat load in terms of course, this is approximate, but still we can do that and we can estimate some kind of a heat transfer load. Thank you very much.